Hiya, I'm Nix, and this video is all about solving the spiral matrix problem on the LeetCode website. As always, solving this problem in the C++ language and giving you a detailed explanation of the entire process, through the planning of the algorithm, to the coding of it, to the analysis of its time and space complexities. If that sounds good to you, then stay tuned. Welcome back. Let's get to it. Given an m by n matrix, we want to return all of the elements of the matrix in spiral order as demonstrated here, as well as demonstrated here in example 2. Now looking at constraints here, here we have that m or n, or potentially both, could be equal to 1. Now those are edge cases that we need to make sure to pay special attention to ensure that our algorithm that we craft handles those special cases. So for planning this out, let's take a look at this example here a little closer. So the matrix has 1, 2, 3 vectors that essentially correspond to the rows here, and the individual values that can be accessed by j are equivalent to the columns here. So i's are the rows, j's are the columns. And looking at the path that we want to walk, we can easily see that there are 4 distinct sections of them. If you're at the top of the matrix, you want to move to the right until you hit this wall. If you're bordering this right wall, you want to move down. If you're bordering the bottom, you want to move left until you hit this wall. And of course, if you're bordering this wall, then you want to move up until you hit the top. So looking at that path, that gives us a pretty good idea of what we have to do in order to emulate walking that path in code. We'll have a while loop iterating through, because depending on the layout of the matrix, we're not entirely sure how many columns and how many rows we're going to have. So when you're not sure how many times you need to iterate, but you know the condition you want to iterate until that condition is false, that's perfect for using a while loop as opposed to a for loop. So we will loop through the matrix and then use additional nested loops within in order to walk the path depending on the conditions, i.e. say if we're at the top I being equal to 0 and we haven't yet reached the right wall, i.e. j is equal to its maximum, then we want to iterate j and push back that value that we see into a new vector that we have. Once we get to that point, we need to essentially adjust the border at the top to eliminate this top row so that the new ceiling of the matrix becomes this row instead, ensuring that we don't overlap any values that we see as we trek across the path. Now those can potentially work for the constraints here of, say, m being 1 and n being something greater than that, and vice versa. But that's probably going to fall apart if we're given an edge case of m and n both being 1 at the same time. But that's really easy to account for in an if statement that occurs before the loops. So if m and n are both equal to 1, then we just want to return that inner vector that only has 1 value in it. And then boom, job done. The last thing to note is we're going to need some variables in order to store all of the information that we need in order to craft the algorithm. So obviously we're going to need that new vector to house all of the values. We're going to need I and j positions, essentially to function as coordinates of where we are individually in the matrix as we walk it. And finally, we're going to need 4 other integer variables that will house where the current borders are of the matrix, where our ceiling is, where our right wall is, where our bottom wall is, where our left wall is. And then after we walk the paths, we adjust them to make sure we don't overlap. Going over this and summarizing before we move on to the code, we have all of the variables that I just discussed. We have that if statement that checks for any edge cases, and we have our nested while loops that function to walk the spiral path here. And with that, let's go ahead and move on to the code. Here are the various variables. The 4 integer variables that represent the borders of the wall. The top and the left limit are set equal to 0. The bottom limit is going to be set equal to the size of the matrix minus 1. So in other words, I want to know what the maximum value of I is. And that means I want to know how many of the inner vectors are present in this outer vector. So I need to loop through that 2-dimensional matrix, the vector of vectors here, and figure out its size. Once I know that, subtract 1, and that's the maximum index that I can have. Similar thing for the right limit here, except instead of looking at how many vectors are in the vector of vectors, I want to know how many values are in one of the inner vectors. To do that, I just grab the first inner vector that's present, so the first vector at index 0 in the 2-dimensional array here, grab its size, and then subtract 1, and then that's my right limit, or how big j can potentially be, j max. Finally, we have position coordinates, I and j, both set to 0, and last but not least, our new vector of integers to hold all of the values in spiral order, which is what its name is. Next up, handling that edge case of both m and n being 1 here. So, if matrix size is equal to 1, if matrix bracket 0 size is equal to 1, then I simply want to return that inner vector that's present, so return matrix at index 0. Next step is before you officially start the nested while loops that start the trek, let's add our starting point to the new vector. So spiral order dot push back matrix 0 0. Now is where our outer while loop starts, and each of these comments is where one section of the path is going to go. So we have a while loop with the condition of as long as the bottom limit is something bigger than or equal to the top limit, and the right limit is something bigger than or equal to the left limit. As long as both of those are true, we're going to continue doing our thing. Here's the section of code that handles one of the paths, essentially when you want to move right. And this basic structure is going to be repeated for the other 3 here. The first thing you want to do is house the while loop in an if statement. Now you'll see the reason for doing this a little later, because I'll point out an example that makes it clear why it's being used. Both if and while have the exact same condition. So as long as I is equal to the top limit and j is something that is less than the right limit. So in other words, we're somewhere at the top here, but we haven't yet gotten to this value that borders the right wall, so j is something less than its maximum. So if those conditions are true, we go into the while statement, and we just want to iterate j and then push back the value that we see. So matrix top limit, or I, both don't change in this section, as well as j. Now, once we get to that right wall, i.e. j has become equal to its right limit, we want to then adjust the ceiling by incrementing up top limit. So we have gotten over here, the ceiling is essentially equivalent to I being 0, but now that we've gone through that 0 vector within the matrix, we want to eliminate it from our future paths as a possibility. So this top limit, which is initially I0, gets adjusted up to I equals 1. Now we have an else if that mirrors the structure up here. Again, both the if statement and the while loop have the exact same condition. In this case, I is less than the bottom limit, and j is equal to the right limit. So we're bordering that right wall, and we want to go down. So again, as long as that is true, we want to increment I this time, and then push back that value that we see with I right limit. Once we've gotten to the bottom, where I is equal to the bottom limit now, we want to adjust that right limit by decrementing it down by 1. So j is initially equal to its maximum value for the right wall. We want to decrease it by 1 to make sure that right wall limit is now here instead. Same thing for moving left here, else if while both have the condition that I is equal to the bottom limit and j is something larger than the left limit. As long as that condition is true, we're going to decrement j, add that value that we see by bottom limit j, and once we get to that left wall, j being equal to the left limit, we want to adjust the floor of the matrix, the bottom limit, by decrementing it by 1. So it shifts it up by 1. Final else if while statement here, I greater than top limit and j being equal to the left limit. Or along that left wall, we want to go up. We decrement I in order to do that, and then push back the value of I left limit. Once we get to the top, we want to shift that left wall to the right by 1, and we do that by incrementing it. Last thing we want to do is after this while loop has occurred, we want to return a spiral order, that vector that we just made after we walk the entire path. Okay. Now that the code has been completed, let's take a look at this outer while loop breaking out after we have completely run the entire path and added all of the values. Now once we have gotten to this point in this example matrix, we've moved right, moved down, moved left, and moved up all once, which have all made adjustments to our borders. And at this point, the top limit of our matrix and our bottom limit of our matrix are both this row right here. They're both equal to 1. Once we move right again and complete this section, we adjust that ceiling down again by incrementing the value of it up. So the top limit was 1 and becomes 2. And at that point, our top limit is now 2, while our bottom limit is 1. So they've crossed over each other. And that means that this condition here in our outer while loop is no longer valid, so we break out of it. And having both of these conditions here makes it such that no matter what the dimensions of the matrix are, as soon as we reach a crossover event for either the top and the bottom, or the right and the left, we know we've traversed our entire matrix and we can break out. And you can see this condition having issues in this edge case here. So what I'm going to do is comment it out, and now I'm going to run this code and see what happens. Everything should work well with, say, this example here. This should equal this, which it does. However, the test case here, I'm going to eliminate all of that and set it up so that m and n are equal to 1. And now I'm going to run the code with that section commented out. And as you'll see, it's going to go on and on and on, and we get a time limit exceeded issue. And the reason for that is because this condition never changes. Bottom and top are both equal, right and left are both equal, and yet none of these conditions present within this while loop are going to end up being valid, because they always have at least one section where we have to be less than a limit. Because of m and m being both 1, that never turns out to be true, thus we never go through any of these if statements and never end up adjusting anything. So this while loop ends up going forever and ever and ever and ever in this case, which is why this if statement is present before this while loop ever gets started, to make sure we don't end up with a situation where we loop infinitely. So I'm going to uncomment that out, and you'll see here, now it should work. Pending, judging, and see? We now get the answer that we want, and we don't loop infinitely. Yay! Next up, let's take a look at the purpose of these if and else if statements. And I'm going to use a test case again to show you what happens when they're not there. So the first thing I'm going to do is comment all of them out. Okay, as you can see, the if-else-if statements are all commented out, so it's as if they don't exist, and the only thing present within the outer while loop are all of these inner while loops. So let's see what happens when the algorithm is faced with this example here, where we only have one inner vector present, and as a result, that means that we're dealing with m being equal to 1, because we only have one possible value for I. So let's see what happens when this is given with those if-else-if statements eliminated. And what do we get? The wrong answer. You can see that for part of it, it does what we want, but then we kind of get repeats added. And the reason it does that is because without these if-else-if statements wrapping around the while loop, while this outer while loop executes, if any condition of these while loops ends up being true, it can go into multiple of them while it's doing one loop. So in this example here, what it happens is it sees this while loop. Oh, okay, I is equal to top limit, j is less than right limit. Yeah, both of those are true. So I go ahead and do stuff and we move right. Then once we break out of this inner while loop, when we continue down on our way, we see this one. Oh, in this case, the condition isn't true because I is not less than bottom limit. But this while loop here, with m being equal to just one value, I is simultaneously equal to the top limit and the bottom limit. And as a result, this while loop has a condition that is also true, so we go into it, and then after going and moving right, we immediately move back to where we were by moving left. So we now decrement j and add it, which is why these values show up when we don't want them to. So the if-else-if statements are present to ensure that only one of these while loops executes during each loop of the outer while loop. Because even though we've adjusted a limit and this condition technically isn't valid, we still need to get to the end of the outer loop and loop back in order to be able to recognize that. But we go into this third while loop before we get that opportunity. So the else-if statements guard against that potential possibility happening. And as a result, I'm going to uncomment all of them. Okay, everything has been uncommented, all looks good. So this time we can now officially start running code, and because I ran code initially, everything should work, so let's just go ahead and immediately submit. And hope for green text, which I get. Excellent. Final thing to do before we look at the rankings here is to look at the time and space complexity. For space complexity, we have created some constant space integer variables here, but what's going to ultimately affect it is creating this new vector of integers. That takes variable space that is going to be big enough to handle housing all of the values that are initially present in the matrix. And the number of values in the matrix is going to be equal to the number of columns it has multiplied by the number of rows it has. So in other words, you want to multiply m by n. Now another thing to note is the presence of the pushback function. The pushback function does have amortized constant time and space usage, but if a reallocation happens, i.e. you've run out of room in your vector to add something to it, so it carves out additional space to make a copy, moves everything over, and then deletes the old one, that's going to have additional time and space complexity dependencies added onto it in those specific circumstances. But because it doesn't happen very often, it becomes, in the long run, overall a constant time and space usage, thus it's amortized. However, to avoid that kind of asterisk of being amortized, you can essentially create this vector with exactly the space that you need. In other words, you multiply bottom limit and right limit and put this in parentheses. and then instead of using pushback, you're going to essentially have another integer counter to log the index of your spiral order, and then just manually add them. That alternate method is more efficient and ideal than using the pushback. But if you don't specify a size for your vector, then you can use pushback easily. So just mention that for future improvements. But keeping in mind the amortized nature of pushback, this algorithm's space complexity would essentially be equal in the long run to big O of m times n because of this vector here. A similar story happens for the time complexity. We have nested while loops present, but they run only enough times in order to completely walk through these matrices. And thus the time complexity for this algorithm is also an amortized, due to pushback, big O of m times n, because it's dependent on how many values are present in the original matrix, and that will dictate the number of times these while loops run. And since they're only doing constant time work present within it, amortized, again, then the time complexity is an amortized big O of m times n. And with that, there's nothing left to do but to click this button and see what the rankings are. Okay, that's interesting. So we don't have a runtime distribution graph at all, and it did not log my space usage, which, as you can see here, is very small range, so I would expect it to ping pong once it actually registers it. So let's see if I can get it to register. Not going to change anything here. Let's try and submit again and see if it actually registers this time. Okay, accepted. Click the button. Hey, it finally registered. Okay, so I showed up right in here, but I fully expect to be able to ping pong around here. And apparently I don't have anything to say for the runtime distribution. And with that, that was how to solve the spiral matrix problem on the LeetCode website. I hope this video helped you out in a way. If it did, consider subscribing. I do these kinds of videos twice a week. And as always, I will wish you happy coding and to have a nice day.